So like we normally do, we'll give you a bit of an overview of our company before we jump into today's content. SimpliPhi Power actually started as optimized energy storage back in 2010. So we started as OES, making products for the film and broadcast industry. In particular, making mobile-based power products that could serve for camera, for lighting, and for things that serve the film industry. One of those items was our Liberty Pack, and we still have Liberty Packs out in the field, still running, outliving their warranty 12, 13 years after we originally produced them. In 2011 and 2012, OES moved into the military industry, and the military was really not interested in lithium batteries at that time. There were safety concerns about, the rugged use that the military would put lithium batteries through, and those safety concerns outweighed the benefits in the eyes of the military. And we were able to put together a series of tests for the military to prove that lithium batteries, especially with our lithium iron phosphate battery chemistry, could be safe and good options for mobile off-grid deployment. And so some of our units ended up being deployed in Iraq and Afghanistan. We continued to work on residential systems as well. We expanded our product line in 2013 and 2014 to have mobile battery-based backup options. And in 2015, SimpliPhi Power relaunched under our current name, SimpliPhi Power. We continue to push out more products. We're always trying to focus on what our customers, what our installers need to make for the best battery-based storage solutions. And so we're continuing to push out more products. In 2017, we really started to ramp up our manufacturing. We introduced high voltage division as well. So we now have a high voltage division. And more recently, about a year ago, we were acquired by Briggs & Stratton. And so that's allowed us to leverage their engineering team and their expertise to come out with a completely new ESS system, which I'll talk just a little bit about at the end of this training. So the problem that exists in much of America and in much of the world really is that we're seeing escalating energy costs, right? The cost of energy, electricity from the grid continues to rise for a variety of reasons. And in the US, we're seeing elevated bills, and we're seeing inconsistency in the grid as well. So there's some failing infrastructure out here in California where we're often having our energy grid shut off. And that's happening often for wildfires or for natural disaster reasons. We also have some failing infrastructure due to age, right? So many of our grid components are aging, and that's reducing reliability. And then, of course, we're all very much aware of environmental factors here at SimpliPhi Power. And there's this need to decarbonize our grid, right? And we see the solution to that as being distributed energy, as people having access to their own energy production, their own energy storage. So our product portfolio is really centered around solving that problem. We use a safe, non-toxic, non-hazardous, cobalt-free battery chemistry, lithium ferrophosphate, lithium iron phosphate. And this is really the battery of choice for home power backup. With this battery chemistry, we're really eliminating that risk of thermal runaway that you can get with other battery chemistries. So those battery fires are not a concern with LFP batteries. We are also UL certified. We have UN Department of Transportation certification for shipping some of our batteries as well, which is great for batteries that need to be airlifted. And so we have some options available there. We're also proven. We've got, again, over a decade of experience, right? We've got 12 years producing LFP batteries. We've been around as long as any LFP battery manufacturer in the US. And so we've got a large amount of history kind of improving our manufacturing process and improving our battery quality. We've been deployed in over 45 countries worldwide. We have over 250 megawatt hours installed. Again, I mentioned some testing at the beginning that we have done with the Army Corps of Engineers, so with the Army and the Marine Corps. And so we've got a lot of history to leverage for a company. We also try to keep our battery solutions as simple as possible. One of the themes for SimpliPhi is to really try to make our batteries work with as many other people's components as possible. And so we try to keep a simple system that allows us to easily integrate with components that are potentially existing already as installs in the field. Maybe you've got somebody who's already got solar on the roof, but they're finally looking to add some battery backup power, which is about 90% of the solar systems, right? Don't have battery backup power yet. And through doing this, we can offer some energy savings as well as resilience and independence in terms of power. So these are countries that we are deployed in. We have distributors across the world, many distributors carrying our product. Of course, we're heavy in the Americas. We do our manufacturing in Oxnard, California, and so our batteries are shipping out from there. We have a big presence on the West Coast, but also throughout America and the Caribbean now. And we're moving into Africa. We've got installs and distributors distributing our product in Australia and some places in Europe as well. So as an overview of what we're going to be talking about today, we're really planning to spend some time talking about how PV systems couple with battery banks. So solar panels are coupled to a battery bank through inverters, charge controllers, and we're going to talk about the two principal means of doing that. One of them is AC coupling, and AC coupling is really referring to having microinverters on a PV array. So PV arrays all produce DC power, but you can put microinverters on solar panels and change that DC power being produced at the photovoltaic cell level into AC 240 volts that can be directly used by the house. DC coupling is really the original way that most systems have been coupled with batteries, and DC coupling refers to the use of taking that power off the solar panels directly as it's produced and using charge controllers in order to take that power and put it into batteries. And so we'll get into that. So let's start off with DC coupling. DC power from generation sources, I mean, these could be, most often we're talking about DC power coming from solar panels, but there are other ways of generating electricity as well, and we'll talk a little bit about wind and hydro. But for the most part, we're talking about PV here. So we're going to talk about using charge controllers that are going to regulate the DC voltage and amperage, and doing that, they can optimize the amount of power we're able to get out of the solar panel. There are some considerations to think about with DC-based systems. And as you can see in the bottom left of that picture there, there's a little bit of shade on that panel there. When you have panels connected in a DC format, you string them into series that we call strings. So we have a number of panels connected in series, and those panels connected in series can only output power if all panels are producing current. And so if you end up having shading on one panel, it can affect the entire string. And one way to think about this is to think about electricity flowing through a wire that has a switch in it that could be turned off. Even though that wire is still there, even though the potential to push the power is still there, if there is some blockage, like shading on an individual panel, that can throttle down the entire string. And so that is a consideration to think about. There are some ways around this. There are what are called bypass diodes, as well as DC optimizers, and we'll talk about that. Some of these issues with DC coupling don't exist with AC coupling, but when you do AC couple, there are some drawbacks to that as well. So shading is certainly a consideration to take seriously when you're looking at DC coupling systems, making sure that you don't have a single shaded panel that's blocking your entire string. Maybe you have a string of 8 panels and one individual panel's got shading. It can take all 8 of them out. We're also going to talk a little bit about open circuit voltage and short circuit current, as well as VMP, that's a voltage at the maximum power point, and the current at the maximum power point. Another thing to keep into consideration for solar panels is that the lower temperatures actually increases the short circuit voltage of the panels. So the panels, the current running through the panels is controlled mostly by the amount of sunlight that they're getting, but the open circuit voltage of the panels, the voltage coming out of the panels, increases with low temperatures. So you'll have to consider that when you're putting your arrays into systems. If they're going to be in places that can get very cold in the wintertime, the voltage can actually go up. So the way that solar panels really work is they're composed by many individual solar cells. And each of these individual solar cells absorbs sunlight, and based on the semiconductors that are inside the cell, they're typically, solar panels are made by having a thin, transparent p-doped semiconductor on top of what's called an n-doped semiconductor. And the way that works is it produces a small electric field, and when light is absorbed, that creates free charge carriers in this region between those two semiconductors. Based on the difference in the electronegativity of those two materials, you basically have electrons being pulled up to the top of each solar cell. And then these solar cells are all joined together in arrays in series in the panel. And that's what those thin strips you see on the solar panel or solar cell are doing. These strips are carrying those electrons from cell to cell. So based on the number of cells in your panel, you can figure out what your voltage is. Typically, with silicon-based cells, you're getting about 0.6 volts per cell. So when we string all those cells together, we're producing DC power out of a solar panel. And regular solar panels without any type of microinverter on them are basically just pushing out a DC voltage and a DC current, right? And so how do you use that to charge batteries? So in a DC coupled solar system, we use charge controllers, and the job of the charge controller is twofold. One, the job of the charge controller is to regulate the output voltage so that you're charging the battery at the correct rate, right? We don't want to charge a 48 volt battery with 128 volt DC coming out of a solar panel. We want to regulate that voltage so that the current comes in at the right rate so that we don't damage the battery. The other job of a charge controller is to try to get the most energy possible out of a solar array. And we do that with two different methods. One method is called maximum power point tracking. So those are normally the most common type of charge controllers for bigger home-based systems. MPPT, you've probably heard that term. And Chuck is going to talk a little bit about what that means in a minute. But there's another type of charge controller that exists. The second type of charge controller is a bit cheaper. It's PWM controller. And these controllers are often used in smaller, cheaper systems. So I will spend just a bit of time talking about how they work. The MPPTs can be very efficient, making solar panels run at pretty close to 99% of their max output level. And the way they do that, well, the charge controllers work in a couple of different ways. So a PWM-based charge controller works by varying what's called the pulse width. So the graph that you see on the right side of the screen there has a vertical axis which specifies the voltage coming out of the charge controller that the battery sees. And on the horizontal axis, you have time. Keep in mind that this is very zoomed in, and these things happen many, many times per second. But the way that a PWM controller controls the voltage coming out of the charge controller is it basically gives a high voltage for a short amount of time, followed by gaps in that voltage. And so if you take that higher voltage and you average it over time with those gaps, the average voltage seen through time is a lower voltage than the total amount coming out of the solar array. And so you're basically turning the signal from the solar panels on and off, on and off, on and off, and many, many times in a second. And when you do that, you can get an average voltage that is decreased that can match the voltage the battery needs to see. I'm going to let Chuck talk here a little bit about an MPPT, and what you can see there is a IV curve there. So Chuck, do you want to talk a little bit about MPPTs?
Thanks, Nathan. Yeah, so for a maximum power point tracking, which is what MPPT stands for, we can visualize this IV curve, which is current on the vertical axis, voltage on the horizontal axis. So if we were in the upper left-hand corner with a short circuit current, that's basically a module connected to itself, you're going to have the highest possible current and low voltage. We know from Ohm's law that if we multiply that very high current by 0, our power is 0. Similarly, on the lower right-hand corner, where we've got VOC, that's the open circuit voltage. So if you had a solar module and you had the positive and negative leads open air, and you took a measure with the voltmeter, that would be the highest possible voltage. But because they're not connected, current is 0. Again, from Ohm's law, we know that that high voltage times 0 means power is 0. So when we look at the IV curve, what we're doing is we're following the red line to the knee. And where that spot on the knee is going to be our maximum power point, where we can get the highest possible power between the voltage and current. So, you know, if we're cruising along this line, current's still very high, voltage is starting to pick up. You can see the blue line is increasing. When we hit that knee where the dot is, that is our maximum power point. And as we continue to increase voltage, our current actually starts dropping off. So what an MPPT device, it could be a charge controller or inverter, is doing is it's riding that knee. It's looking for that highest possible power point, making slight adjustments in real time, saying, okay, if I'm right here at 56 volts and I go to 56.1, do I get more power or less? Likewise, I could drop down to 59.9, and do I get more power or less? So, you're able to ride that curve for the maximum power. This is really handy when we're dealing with shade, because like Nathan was saying, in a DC string, shade can affect the voltage across the string. If the voltage is coming down, we don't want it to just collapse and not have power. So by riding the best part of that knee, we continue to maximize the PowerPoint technology. So once again, these are using string inverters, micro inverters, DC optimizers are all using this technology, as is an MPPT charge controller. And Nathan, you're still muted.
Thank you, Chuck. Yeah, and I think what's going on here too, right, is to remember that, with this IV curve, when you're pulling more current out of a solar panel, the voltage goes down. And that's what's happening with the knee there. If you pull too much current out of your solar panel, you get down to a point where you're ending up at a short circuit condition, right? And the voltage is essentially goes to 0. And so the controllers are pulling a little bit more current and a little less current and seeing what happens to that power output. So how do we couple a DC-based system? Here is an example where we're showing that we've got an inverter on the left side, so that this is a Victron inverter on the left side there, and that's coupled with loads from the house. It's also coupled to the grid. And a DC coupled system is going to take the energy from the solar panels, have that come into the charge controller. And so you can see an MPPT 75 there. That's going to allow current to come from the solar panel. It's going to regulate it and send that down to the battery. So it's important to note that the batteries here, the charge controller, and the inverter are all coupled through this DC bus, right? And so the DC bus is there as a way for us to ensure that the batteries are all seeing the same voltage from the charge controller. They're all charging together. It's also a place where the inverter can be drawing power off from those batteries and feeding it back to the grid or feeding it to the loads when the battery's energy storage is needed to power the house. This is the bus, and it's important to connect to that bus with cables of equal length to the batteries. Here's a single line diagram that shows you a DC coupled system. And one of the things about DC coupled systems is that we need to have the ability to shut those off. And so what you see here is a Tigo rapid shutdown devices. And we have a signal generator that's here. And what the signal generator is doing is receiving a 12-volt signal from the Solarc inverter. And that's called a keep alive signal. And so as long as the Solarc is being told that everything is fine, the system should stay alive, it's sending that 12-volt signal to this Tigo controller, which ends up telling these Tigo controllers, these rapid shutdown modules, to keep the solar panels alive, right? And some of these rapid shutdown modules have built-in optimizers in them as well, so that if you do have shading issues, it can turn off that individual panel and bypass it and send the signal directly to the next. And so these optimizers also allow you to avoid some of those shading issues. What you can also see here is that this is our DC bus here. This is our combiner box. And this is allowing two large, these are our BOSS 12 cabinets to be coupled with this Solarc inverter. And so what the inverter here is doing is it's got built-in MPPT charge controllers. It's charging these batteries off of that solar array when that energy is available. You'll see that there's also a critical loads panel here. And this is a grid-tied system where we're connected to the grid through the main panel. Let's talk about AC coupling. So unlike DC coupling, AC coupling, you don't have quite as many shading issues, because with an AC coupled system, each of the solar panels has a microinverter built into it. All of these microinverters are running in parallel with each other, so that when one system goes down, right, when one system has shading, it doesn't affect the other solar panels because they have their own microinverters producing that 240 volts. So what's happening with microinverters on the roof is that you basically are going straight from, at the solar module level, straight from that DC production from the PV into a microinverter, a PV inverter, and that's sending that 240 volts down. And oftentimes, these are directly connected to the loads of the house and to the grid. If you want to add battery backup, however, you need some way to turn that AC signal back into DC. And so that's what the battery bank inverter does. So for an AC coupled battery backup system, we need to have a battery backup inverter. And that battery bank inverter is what's going to convert that 240 volts of AC back into DC power to be able to charge the DC batteries at that typically 48 volts. Occasionally, there's still some 24 volt coupled battery systems. So it's essentially using an AC coupled solar is really the same as using a generator. It's not much different. And typical inverters actually will use the same port for both generator charging or AC coupled solar charging. How then can power coming out of the solar array be regulated? How can a battery tell an AC coupled solar array how quickly it wants to be charged? Right? So these solar arrays that are on the roof, you can't slide up and down the IV profile like Chuck was telling you how you could do for DC coupled systems on MPPTs. So the way that a battery can control the output power from the AC coupled solar panels is to do what's called frequency shifting. So let's suppose that the grid goes down, right? And let's suppose that we've got our AC panels on the roof with a battery backup system. Normally, if a grid goes down and you don't have battery backup, AC coupled solar panels shut down. And that's one thing a lot of homeowners don't realize, right? Is when the grid goes down with an AC coupled system, if you don't have battery backup, then you're not going to have any power from your AC coupled system. The only way that an AC coupled system will work, right, that would just be a grid tied AC system. The only way that you can get power out of that is when you have a 240 volt AC signal, and that can come from the grid. But if we have battery backup power, then that signal can come from the inverter itself. So the grid is down, we're charging our batteries based on the AC signal there. The way that we can regulate the charging cycle is to shift the frequency. And so instead of running those panels or running that inverter directly at 60 Hertz, we might bump up that frequency just a little bit to maybe 60.2 or 60.4. And that can tell the microinverters to charge the batteries a little bit slower, right? Additionally, if the batteries are full, the loads are not drawing enough, and we want to tell that the AC coupled solar array to shut the microinverters off, we can actually frequency shift maybe all the way up to 62 Hertz. The system will then say that, hey, the frequency is out of range, and the microinverters will shut down. So using frequency shifting, we're able to turn these microinverters on and off. So here's an example of just a straight AC coupled system. There's no, or sorry, just a straight, an AC coupled system where we're going directly. This is just a grid tied AC array, really, because we don't have batteries in it yet. If we want to add batteries in there, we have to have a second inverter. So these solar panels have microinverters mounted to their backs. They are producing DC voltage. The microinverters turn that to 240 volts AC. That is coming down to a separate disconnect box here. And so I've got this AC signal coming in. If I want to charge batteries, I have to have that second inverter. And that's what the SolarArc is doing here. I have a second inverter that allows that AC signal coming from the solar panels to be converted into DC to charge up the battery bank, the DC battery bank here. Let's talk a little bit about some applications. For off-grid systems, you're almost never going to use AC coupled solar, right? It really doesn't make sense. DC coupled solar systems are a little bit more efficient. We're taking the DC energy from the solar panels and directly using that to charge DC batteries. So we're not having to convert the DC signal into AC and then convert it back into DC to charge the batteries. Each time you do that, each time you do this inversion process to switch DC to AC, you lose some energy in the form of heat. So most off-grid systems are going to feature DC coupled battery banks, and those DC coupled battery banks are typically going to be run with MPPTs. When you have a off-grid system, you're not really having to deal with grid power, right? So there's no grid in an off-grid system, but let's suppose we're in a grid-tied DC coupled solar system. When the grid does go down, the inverter now can pull DC power out of those batteries and create an AC signal, but we don't want to send that signal back to the grid, right? If there are linemen working on the lines, we need to make sure that our system is not feeding AC power back up to the grid. And so we have to have a transfer switch built into the inverters. And so the inverters are basically isolating themselves so we don't have an island condition where we have a production of AC that's feeding to the lines that can harm people. So for battery backup systems, typically you could have solar arrays that could already be existing. And so for existing arrays where you have AC coupled arrays to begin with, then you might consider, instead of removing all of those panels and getting rid of all those microinverters, the real cost-effective thing to do here is to add an inverter and AC couple the system. You have a little bit less control over AC coupled solar systems in terms of using the energy. And those limitations come naturally from having that AC signal, having to use frequency shifting to control the AC coupled solar panels. So for existing PV and AC coupled systems, so if you have an existing PV with AC coupling, you have some challenges that you have to pay attention to. So islanding mode is one example where we have to make sure that we're not feeding back into the grid. There's this misconception that you can't add battery backup to an AC coupled solar system, and that's not true. Many of the inverters that are out there are capable of using, and typically through the generator port, they're capable of using that AC to charge batteries. And so I want to make that clear that it is possible to do that. When you have an AC coupled system, you don't need optimizers that are built in. Additionally, the inverter is capable of controlling the AC output from the microinverters, and so you also don't need to have those rapid shutdown modules. It's a good idea to check with your local housing jurisdiction to make sure that when you do have a DC coupled system, almost everywhere you go in the US now, you're required to have those rapid shutdown modules on your array. And that's to prevent damage to harm to anybody who might be working on the system. If there's a fire at the house, et cetera, they have to have a way to rapidly shut off the array at the solar panel level. Let's talk a little bit about rapid shutdown. So for a DC coupled system, you need to have some type of way to shut the panels off at the panel level. And so that's the module level shutdown. And the way these work is you have a keep alive signal coming from the controller system, whether it's a Tigo or another brand. And that keep alive signal is basically keeping a rapid shutdown module switch closed so that you're continuing to get the power out of that switch. If that keep alive signal gets tripped, then that rapid shutdown module tells the keep alive to shut down, and that shorts out the solar panel, and you're no longer getting power. For AC coupled systems, again, as I said, you don't need to have that inline rapid shutdown module there to stay in compliance. It's not required, but you do need to have a string. You do need to have do need to have oftentimes a switch which would allow you to shut off that AC system. So here again is an example of a DC coupled system. We have that optimizer. We have these optimizers that are on here to help us in shading conditions. We have a DC disconnect here to turn the system off. And additionally, we have this rapid shutdown module as well. So here's just a simple button. This button is to control that rapid shutdown. When the button is pressed, it tells the keep alive signal to stop being sent. Once this stops sending the keep alive signal through the solar wiring, then these rapid shutdown modules will shut down each of the panels at the panel level. Here's an AC coupled example. We still have the switch that I was talking about you still have a disconnect here for the AC coupled system, but notice we don't have to have any keep alive signal here to tell these AC coupled systems to shut down. In fact, when the grid goes down, these microinverters are no longer seeing an AC signal, and once they don't see an AC signal anymore, they will shut down automatically. But let's talk a little bit about system design considerations. So with a DC coupled system, you need to make sure that we're setting up to charge the batteries at the correct rate. We want to limit the rate that the batteries are charged so that we don't damage the batteries, and that's done at the charge controller level. And a lot of the new systems will have the MPPT charge controllers built directly into the inverters, but if not, make sure that you're using an inverter that you can program the charge controller directly to match this battery bank that you have. There's also the consideration of the wiring runs. So many systems have limitations on how high the voltage can be for the DC coupled solar array. So we string the panels together in strings, and that string voltage should not exceed the maximum voltage of the MPPT controller. Keep in mind, if you have an MPPT controller that maybe has a 500 volt maximum open circuit voltage rating, that in cold environments, right, your solar panels open circuit voltage will typically be higher than the open circuit voltage that's on the label. So the open circuit voltage on the label of solar panels is the voltage those solar panels will be putting out when they're at 25 degrees Celsius, right? So that's a 72-ish degree Fahrenheit temperature. So at really low temperatures in the winter, that voltage can go up by as much as 10 to 20% if you get really cold. And so you'll need to make sure with these DC coupled systems that you don't exceed that voltage. And so typically you'll want to build in a little bit of a buffer if you're in a low temperature, a place that can get to low temperatures. The wiring runs. So it's also the power, as Chuck was saying, right? Ohm's law, current times voltage gives you power. And so if you have a high voltage system, you can actually have less current and get the same amount of power, right? Current times voltage. So if I have a high voltage solar array, I'm typically able to use a smaller wiring and be able to couple my system potentially just with one string or two strings that are at high voltage, as opposed to doing a lower voltage system where I'm going to have to use a lot more current and therefore use bigger wires. So having MPPTs that have a high voltage range is beneficial in terms of making it more efficient and lower cost. With an AC coupled system, the power that is being sent down from the grid level to the inverters and the battery and the loads of the house is being sent down at 240 volts. You don't really have a way to change that, right? Either 120 volts or 240 volts. And so you'll need to size your wiring based directly on that. You'll also want to consider in both systems, if you don't have a large enough system to do a whole home backup, as most customers don't, having a critical loads panel to keep powered on even in the event that the grid goes down. And so that's one of the advantages of having a battery backup system. You can keep some of the loads on to your house when the grid does go down. So for a DC coupled system, typically when you have large photovoltaic systems where DC coupling, if there is shading, we might want to add in optimizers as well. And we want to make sure that we have our rapid shutdown there to be compliant with fire codes and regulations as well. Some very large systems have DC to DC converters, but that is not a very common way to couple batteries into DC systems. On AC coupled systems, you can have large photovoltaic arrays as well. Typically, you're having microinverters where you have one microinverter per panel. Sometimes some of the microinverters allow you to do two panels. It's based on the power output of the panels, right? But you'll need to have, if you have a large AC coupled system, you'll need to have a large scale battery bank inverter to be able to produce the amount of current that is needed to charge the batteries. It's also important, it's harder to regulate power coming out of AC coupled arrays. So it's more important here to size your battery bank properly. If you have a 10 kilowatt AC coupled array on the roof running down to a battery, you'll want to make sure that your batteries can handle 10 kilowatts of incoming power. So it's much more important to size a battery bank based on the maximum output for an AC coupled system. For DC coupled systems, the MPPTs are able to throttle back the amount of energy they're taking off the panels. So let's talk a little bit about our batteries that would be used in AC and DC coupling situations. In fact, really, our batteries don't have a preference for AC or DC coupling. It's the equipment that goes in, right, which controls whether or not, how the batteries are going to charge. And all of our batteries, as I mentioned at the beginning, are LFP. They're lithium iron phosphate batteries. We use only cylindrical form factor in our batteries. We don't use pouch cells or prismatic cells. Pouch cells are just not nearly as durable. Both pouch cells and prismatic cells allow for some expansion and contraction during charging and discharging. And so those heating and cooling cycles can make them have a shorter lifespan. In a cylindrical cell, the outside of the cell is actually a steel container, and that cylindrical form makes it very resistant to expansion and contraction, which makes this cylindrical form factor really the best in terms of durability and longevity, which is why we're able to offer a solid 10-year warranty on all of our battery products. It's also important in many jurisdictions to have our certifications. All of our batteries are certified through UL Underwriters Laboratory. Our cells go through a 1642 testing. Our batteries go through a 1973 testing. And then there's a 9540 system level certification that we have for our batteries and our ESS backup systems. These certifications are needed for meeting building and fire codes in most jurisdictions. The 9540 is becoming more and more prevalent throughout the country. And so it's important to check with your housing jurisdiction when you're looking to install new batteries. We've had people buy batteries and have to return them because the local AHJ and the building inspectors are not going to approve them. And so they've come to us and say, hey, the batteries I originally bought, don't work with my building inspector. I need batteries that have appropriate certifications. And so I've gone through that with tech support with people having to return batteries. So it's important to make sure that those UL certifications are there for the batteries you're installing for your customers. Okay, so our modular scalable batteries, the first battery that I'm going to talk about is our PHI battery. And this is one of our most common batteries. These batteries come in either 24 volt or 48 volt voltages. And depending on they're both 3.8 kilowatt hours, you just get more current out of the 24 volt battery than you get out of the 48 volt battery. This battery is able to be either AC coupled or DC coupled. You need an appropriate battery bank inverter in either case. So if it's DC coupled, you need to make sure that you have an appropriate MPPT built in that's capable of setting the correct charging rates for this battery, which is this battery charges at a rate of C/2. So for a 48 volt system, that would be 37.5 amps of current. And so 48 volt, typically we are recommending that people use 48 volt, and that's really becoming the prevalent voltage for home-based systems. Frequency shifting is done really at the battery bank inverter for charging off of AC coupled systems. Again, I mentioned it's very important for AC coupled systems to make sure that the battery power, the charging and discharging power of the battery, right, matches your solar array. So if the solar array is capable of charging at 5 kilowatts, right, this individual battery is only capable of taking 1.9 kilowatts. So you need to make sure you have enough of these batteries so that the amount of power the solar array is generating is not too fast for charging these. This is our SimpliPhi battery. Our SimpliPhi battery has a similar battery pack to the PHI battery. However, it's got advanced communications built in here. It's got a much more sophisticated closed loop communications enabled battery management system. So all of our batteries have breakers and battery management systems inside them. It's just that this SimpliPhi battery has a much more sophisticated system that can monitor internal cell temperature in many places. It can monitor charging rate, state of charge, voltage, temperature, and send all that information out. Currently, we have this battery being available for use with our inverters, as well as with solar inverters and Sunny Boys. And I think this might also work with Schneider. Daniel or Chuck, can you comment on that? Is this battery communication system compatible with Schneider?
I believe it was SMA and Solarc.
Okay, so SMA and Solarc, and it doesn't communicate yet with the
and our new inverter.
and our new SimpliPhi inverter as well. Thank you. Okay. This is our access energy storage system. And an access system, we're putting both the batteries and the inverter inside an outdoor rated enclosure. And this is really a plug and play, a quick way for installers to put an ESS system into a, into a homeowner's house. It works great for AC coupled systems because obviously your AC coupled systems, everything is already outside. So this is an outdoor rated unit where everything is already kind of ready to go, real plug and play system for installers. So you mount this on a concrete pad outside the house, near to having a critical loads panel and connection to the grid. So you can do AC coupling with this, with either the Solarc MPPT, either with the Solarc or the Snyder coming in this inverter, coming in this access unit. Pretty soon, we're going to have our own SimpliPhi system being available in the access cabinets as well. Again, the rate is a C/2 rate for the charging of our batteries, and you'll probably want to use a critical loads panel to take power out of this as well to keep that home backed up when the grid is down. So this is what this looks like inside. There's an automatic transfer switch that's built in. So this Solarc unit will sense when that grid is there. If that grid goes down, whether or not you're AC or DC coupled, if that grid goes down, this Solarc will kick on, power those critical loads off of the batteries in a fairly seamless transition. This is easily set up for permitting. Their 9540 is already completed there. Sorry, it says 9450. That's a typo there. 9540 is completed for this unit. It's ready to go, and it will has all the certifications that almost any housing jurisdiction will need. The maximum power that you can get out of this Snyder access, it depends on the number of batteries that you have installed there. It's 3.9, a 3.8 kilowatt hour battery will do 1.9 kilowatts of power, right? You can get up to 6 of these in the system. We also have an additional system called our boss cabinets, where you can get up to 12 additional batteries in an outdoor rated enclosure as well. I'm going to take just a second to talk to you about our new ESS system. So like I said, this 6 kilowatt inverter that Briggs & Stratton has released with SimpliPhi is going to be available in our access cabinet soon. But if you're looking for outdoor rated batteries, we also are offering our new 4.9 kilowatt hour battery. It's also got an advanced BMS, just like the SimpliPhi, where it has closed loop communications built into it. This battery communicates seamlessly with our 6 kilowatt inverter. These units are stackable, so we can parallel them. Up to 9 inverters can be paralleled to give you 54 kilowatts of continuous power, and up to 72 of either our SimpliPhi batteries or this new SimpliPhi battery can be put in parallel to give you a huge amount of storage. I think that's 358 kilowatt hours of battery storage there. And this new ESS system comes with the Energy Track app, which allows installers to do fleet management, right? So installers have access to all of the ESS systems that they've installed. They can remotely monitor them, remotely push firmware updates to those systems, communicate with the customer any needs for servicing that their ES system might have. So the 6 kilowatt inverter, as I was saying, you can scale up to 9 of these to get 54 kilowatts of power, but each individual inverter is also capable of surging. And the individual inverters can surge for up to 5 seconds at 50% extra. So you can get 9 kilowatts of power out of this for 5 seconds for starting something like a well pump. And the instantaneous power is actually 12 kilowatts each, just for a fraction of a second. So you don't get some early error code when you're trying to start something that's just a little over 6 kilowatts. Additionally, like I said, you can get 9 of these paralleled up for 54 kilowatt system. I haven't seen anybody do one that big yet, but we have systems where people are coupling. We have 2 of these in our office that we have coupled for 12 kilowatts of power to power our office building. Transfer time here is 8 millisecond switchover, which is very fast, right? That's 8 1,000ths of a second. That's faster than 1 100th of a second to switch over. So you really won't notice. This can operate as an unlimited power supply. You won't notice the light flicker. The internet connection should stay stable. Clocks won't need to be reset, etc. And this is coming with our 10-year warranty. Again, it's an outdoor rated system. Our battery, our 4.9 kilowatt hour battery, is a wall mountable battery. We're giving our full 10-year warranty on this as well. Like I said, outdoor rated, can be mounted directly outside with an AC or DC coupled system. Our inverter can be used for that, or you can use a solar arc, etc. And again, scalable up to 358 kilowatt hours. That's huge. Closed loop communications built in. And so the Energy Track app allows you to do a very fast commissioning process. I've heard from distributors that the end-phase systems are sometimes taking hours to do their commissioning process. We're able to use this to do a 5-step commissioning process, which includes setting up your homeowner's Energy Track account, right? And we've gotten that down to about 12 minutes for commissioning. So it's a really quick way to commission a system. You can connect to this, to the gateway through a Bluetooth, Ethernet, or Wi-Fi. So we've got some flexible connectivity there as well. We also have, so if you are designing a AC or a DC coupled battery bank, we have a battery sizing tool on our website. We have lead acid replacement sizing tool. So there's a big difference, as most people know, between using a lithium batteries and lead acid batteries. And so we have a sizing tool to help you there. With a lithium battery, you can draw our batteries all the way down 100% depth of discharge. You would never do that on a lead acid battery. And so these sizing tools are available, and I'll be sending copies of this slide out so that everybody has these links after our talk. We also have integration guides and manuals on our websites, as well as the spec sheets for all of our products. So I want to encourage you to look at that support section of our website. Integration guides tell you how to use our batteries with other people's equipment. And if you're doing an AC coupled system, it's important to be able to do that. And so we have those integration guides that are there. So with that, I'll just mention one last thing. As many of you might be installers, we have an elite installer qualification program. This program allows us to give $25 back per battery installed for our Elite IQ installers. We're sending those checks out. We're sending checks out now. Chuck, Daniel, and I are processing these battery rebates at this time. And we've got many people that, have installed 75 of our batteries. We're giving them checks for $25 per battery back, right? So we have this battery cashback award for our IQ installers. You can become IQ certified by filling out one of these qualifications applications on our website. So I encourage you to look for that as well. There's additionally a $250 photo contest for that as well. So the link to become an IQ installer for SimpliPhi, we'll put you on our website. The link is there. Sign up for that program. We would love to have you join, and we can get you some perks for that as well. So thank you for your time, and I'd like to take some Q&A now. So
yeah, Nathan, we've got a couple questions here.
Great.
Can you explain how a hybrid inverter is different from an AC and DC inverter? So yeah, what our SimpliPhi ESS is a true hybrid inverter. You can AC couple, you can DC couple, and you can have the ability to be grid connected. So you've got all those features. A typical string inverter that's only grid connected may not have that battery backup capability. And likewise, there may be some battery-based inverters that don't allow you to connect to the grid for cell export.
Yeah, and the hybrid inverters, most of the hybrid inverters have those built-in MPPTs as well, right? So a hybrid inverter is really there to help you couple batteries into a system, right?
And there's a second part of this question I'm not sure I understand. I believe it's asking about power control systems and working with different voltages of a PV panel. Those are really two different things. The voltage of the panel is really going to be how we're working on charging the battery. Power control systems are going to be more of a, breaker sizing. You may be able to, if you're in an NEC 2020 code land where they're adopting that code, you may be able to avoid some 120% rule downsizing of main breakers or working on AC bus bars via power control systems. If I didn't answer that question, please go ahead and clarify in the questions.
Okay, good. Yeah, and so the anonymous attendee here has said, cold weather increases VOC. Yes, that is true. So what's happening inside a solar panel is you have these buildup of electrons, right? And as Chuck had told you, if you're not drawing any of that charge off of that panel, you end up getting a maximum kind of density of charge carrier on the solar panel, to the point where any more charges building up would kind of be repelled from the existing ones. And so that voltage actually depends on temperature. And so if you go to lower temperatures, you are able to get a higher charge density on the solar panel. And so that 0.6 volts that I gave you at 25 degrees Celsius, that actually can go up to somewhere around 0.64 volts if you drop down by about 25 Celsius at 0, right? So at freezing temperature of water, right, that voltage goes up by about 5%. And if you go to even lower temperature, it goes up even more. So yes, VOC, the open circuit voltage of your panel, right, increases with lower temperature.
Yeah, Nathan, you spoke correctly throughout the webinar, but I believe we have a typo on a slide that we will correct for anonymous attendee here.
Thank you, Chuck. Thank you, Chuck. Okay, Jeff asks, I understand SimpliPhi batteries can be used with different brand inverters. Sorry, I missed it. Inverters / charge controllers. Who makes the Briggs inverter? So the Briggs inverter is an inverter where we're using a globally sourced manufacturer to make our inverter, but we're working with the software on that. And so we are making that inverter in collaboration with a global manufacturer. And so we're also, we also have the ability to couple with our own inverter, of course. And I didn't mention that a whole lot of times throughout our talk today. But our inverter is also capable of doing AC coupling of solar arrays through our grid port, which will give you up to 40 amps of AC coupling. All else considered equal, which produces the most power at the solar module level if there is shading? Solar module with optimizers or a string inverter, or a solar module with a microinverter? That's a great question, Ruth. I think that the answer really is that a AC coupled system with a microinverter on it works in a very similar way to a standard traditional inverter that has DC optimizers. So whether you've got microinverter or whether you have DC optimizers there, the only thing that you're really doing is cutting out those individual cells or individual solar modules, right, where you're not getting any current out of them. And I think that it's probably pretty even as long as you have the DC optimizer on there. The micro inverters are a little bit more expensive. You're looking at several $100s per micro inverter, but the DC optimizers, you're looking at more like $50, right? But then again, go ahead, Chuck.
I might add on to that and say that depending on the micro inverter, you may actually experience clipping. If you have a 320 watt microinverter on a 400 watt panel, that microinverter can only ever push 320 watts. So, when you're talking about the most power at the solar module, like Nathan was saying, it's probably going to be a DC optimized or string. When you start throwing in shading, those module level electronics take care of that for you. As long as the electronics are capable of handling the power output of that module. So it's something to be aware of. You could slap a microinverter on there and think you're fixing shading, but you've actually introduced clipping. So there's some give and take there.
and as he's saying, you know, typically the microinverters are not capable of inverting the full amount of power of a solar panel. And unless you're under full sun conditions, you might not need that. Ruth, you ask another question. You say, if we recommend no less than 20% depth of discharge, why not show the rated energy as 80% of 3.8 kilowatts? And the answer is we give you a 10-year warranty and allow you to do 100% depth of discharge. We recommend 80% so that battery bank will last as long as possible. And so at 10,000 cycles, sorry, at 80% depth of discharge, we expect you to get 10,000 cycles out of the battery, which is 27 years. At I think at 90% depth of discharge, we drop down to about 6,000 cycles. And if we do 100% depth of discharge, we expect you to get 4,000 cycles. Either way, if you're discharging our batteries 100%, we still give you a full 10-year warranty. But we'd love to see these batteries in the field for 20 years as opposed to just 10, right? We love to see them outlasting our warranties. How is the access affected by extreme cold weather? Is it insulated? Is it heated? So good question, Richard. We do have heating solutions for the access cabinet. We have heating pads that can be coupled directly with our batteries. So if that is something that you need, let us know, because we can produce our access cabinets with heating pads that go directly under the battery. We've had people insulate the inside of the cabinets as well. Remember, the inverters, the charge controllers, and the batteries themselves all produce heat. So typically the battery temperature is significantly above external temperature, especially, you know, if you throw some insulation under those battery cells. We have a whole training around using our batteries in extreme environments. And like I said, one of our options is to have heating pads that work with our batteries, and those get wired directly into the battery with a thermistor controlling the heating pad. So that's one option. And if you'd like more options, please email us at training@simpliphipower.com. Additionally, for those wanting NABCEP credits, the email address is training@simpliphipower.com. Kelly asks, is this inverter a 120 or a 240 volt output? It's 240 volts, but split phase. So that means you get 120 volts per leg, but 240 volt output on the SimpliPhi inverter. Thanks for the question. Ruth asks, just wondering, as we all know how loud our neighbor's AC sounds, what kind of noise at what levels can we expect from these units? The SimpliPhi units are pretty quiet, and I'm not sure if you're talking about our inverter. So our inverters are pretty quiet. We have 3 cooling fans inside them, which means that they can run at a slightly lower rate than just having one big high-powered fan. But if you're talking about the access cabinets as well, the sound of the access cabinet, right, it depends upon the, you know, whether or not those fans are running. And so we have some different options in terms of fans, but I wasn't sure if you were talking about our inverters. So if I didn't answer your question, please clarify.
Yeah, Nathan, the SimpliPhi
ahead,
inverter spec sheet rates our noise level at below 50 decibels. For comparison, that's about the level of a fridge. So they're not super loud. Thanks,
Chuck. That's a good answer. Ruth also asks, a standard household access unit. So I think that's what she was talking about, was the sound level of the access units. Our specifications page on the access cabinets, I believe, also has the decibel rating of those fans. Has SimpliPhi put process in place to enable component reclamation, recycling for sustainable end-of-life practices? So for practical reasons, recycling needs to be done at the local level. It doesn't make sense to ship 90-pound batteries across the country. However, we have gotten in touch with people. So if people don't know where their recycling centers are that do recycle these batteries, Keep in mind, our batteries don't have the cobalt in them, so they're a little bit easier to recycle the lithium out of. So if you need help getting in touch, you can send us an email and we can help you get connected. But yeah, there should be local options for recycling batteries. And unfortunately, we don't have a way to reclaim these batteries by having you ship them back, just because the shipping cost is too high for users to do that. Your tools and user guides are fantastic. Thanks, Ruth. We'd love to hear that. Our customer support team really works hard to try to give good customer feedback. And so encourage you to continue to make use of that. Call our tech support if you have any questions or need help. And additionally, I'm happy to connect you with sales application engineers if you need help sizing your systems. You've got a specific issue that maybe your distributor is not able to answer, call us. We'll put you in touch with our application engineers to help you with designing as well. Simba asks, is your inverter now available on the market, and what technology does the inverter use? Yes, it is transformerless, so it's a transformerless inverter. I'm not sure about the other question you have there, high frequency or IGBT. Chuck or Daniel, do you know how to respond to that one?
You know, an IGBT is an internal component, and I don't have information on the what we're using inside our inverter, whether they're FETs or IGBTs. But yeah, it is a transformerless inverter, and yes, it is available on the market now.
Yep. Sorry, I have no extra input.
Thanks. I saw Snyder in one slide. I have a Connect system with a battery monitor, MPPT controller, and inverter. All communicate with Cat5 cable. Will this system now or eventually communicate via Cat5? Yes, both our SimpliPhi battery and the new SimpliPhi battery communicate with Cat5 or greater cables, right? So Cat5, Cat6 cable, you can use a standard Ethernet Cat5 cable to communicate with our batteries. And yes, thank you. So we got to thank you, said great products. Glad to hear that positive feedback. Can some hybrid inverters regulate power to the battery bank and thus make battery bank size match to solar PV output not as important?
Yes. So in the instance where we have closed loop communications with, for instance, a Solar converter, the Solar can curtail PV production to match an undersized bank. It's one of the few instances where we'll let you actually undersize to a solar inverter. Now, for an Outback Radian, it's an 8K inverter. It doesn't have that ability. You have to have 8K worth of battery power capacity. You have to be able to push 8K into that inverter. In some inverters, you may be able to regulate via the screen, but that's one of the really cool things about closed loop communications, is that the bank can actually tell the inverter what it was willing to accept as a charge.
Great, yeah. And so that's both our SimpliPhi battery and the new SimpliPhi battery. So the advantage of the SimpliPhi battery is it's an outdoor rated battery. The advantage of the SimpliPhi battery is you get a little bit of cost savings. It's not an outdoor rated battery, but you get all of those communications built in with both of those batteries. And so the battery is telling the inverter how it wants to be treated. And so that communication is set there automatically by the closed loop BMS connection. Okay, Ruth says, good point about the clipping. Thanks for reminding you. Yeah, sure. And Newt says, regarding SMA Sunny Boy inverters, can you explain how you would integrate with SimpliPhi batteries? Sunny Boy to Sunny Store to series string, 100 volts DC minimum of SimpliPhi batteries is one option. And then, of course, AC coupling of a Sunny Boy direct to your SimpliPhi inverter. Newt, I'll have to ask you to contact us, and happy to talk to you about our connections with Sunny Boys. If you want a quick answer of examples of how you would connect with the Sunny Boys, those are in our integration guides. So if you click on support and then click on integration guides, we have an SMA integration guide. And that gives you some options of ways to connect with the SMA products.
And if I may, I believe, Newt, that one of the solutions is going to be to use the SMA Sunny Island. You know, your Sunny Boy is a grid-tied inverter. It's not a battery-based inverter. So you could use a Sunny Boy with our new SimpliPhi ESS. It does AC couple to an existing grid-tie inverter. But to Nathan's point, if you have specifics about integration, check out our integration guides or reach out to our sales applications engineers. We can put you in touch with them.
Yeah, and I think what he was asking is if he already has a Sunny Boy there, what could he do to bring battery back up? And that's why I was saying the integration guide should help you. And so it looks like, can you scroll? Let's see, let's go down a little bit. So Ruth has said, wow, great answer. Comparisons are very helpful. Glad that you can help people because the uncertainty sometimes make people just dump components at the end of life. Yeah, we don't like seeing stuff go into the waste as well. I will say that as batteries are becoming more and more popular, you're getting more and more options for recycling and reclaiming that lithium. I don't know as much about the cobalt recycling and cobalt-based chemistries, but luckily SimpliPhi doesn't use that. And that's actually one of the reasons we don't use cobalt. You do get a little bit higher energy density out of them, but then again, it's environmental considerations matter to our team. Alan says, thanks for the webinar. Ruth says, do all your systems have online real-time monitoring of battery state of charge, current solar charging, etc.? So we only are offering one inverter right now, but yes, that inverter does have real-time monitoring for battery, SOC, temperature, power production from the solar array, power production from generator, and that's in the energy track. And you can view that energy track manual on our website as well, and it'll tell you about the specifics of that monitoring. So I want to thank everybody. It looks like we've gotten to the end of the Q&As. We still have 60 of you on here. I want to thank you for your time. Love having the questions. It's really my favorite part about doing these trainings is hearing your questions and sometimes getting stumped. So if you have questions that you didn't get asked here and you would like to ask them, training@SimpliPhiPower.com. Remember to spell that phi with a PHI. So thanks, Joe. Thanks to all of you. We appreciate your time today. Bye, everyone.